Hello, math application students, and welcome to your online lesson. Today we will be talking about the chi-squared goodness of fit test. Our learning intentions include learning to perform and interpret a chi-squared goodness of fit test, and then also to identify the differences when using a goodness of fit versus a chi-squared independence test. We'll know we're successful when we can use the chi-squared goodness of fit test to determine if sample data is consistent with predicted or expected data. So our first question is obviously, what is the chi-squared goodness of fit test? So the chi-squared goodness of fit test is a test that is applied to a single categorical variable from a single population, and it's used to determine if the sample data is consistent with a hypothesized or expected distribution. So what does all that mean? So when we did the chi-squared test for independence, we had two variables within a single population, maybe comparing age and performance or something along those lines. Here we're just looking at a single variable, a single category, if you will, a single way of describing something that can have many options. And then we're just seeing if it's consistent with predicted or hypothesized or expected data. And we use the word distribution there because, again, maybe we don't expect them all to be equal. We expect them to vary depending on the different choice they make, but we have a certain prediction within that variable that we expect. And that's what we're looking for. And we'll make a little more sense of that when we get to an example. So how is the chi-squared goodness of fit test different from a chi-squared test for independence? Well, they do have certain similarities. In fact, obviously, both of them are going to use chi-squared, and the math involved in finding chi-squared is essentially the same for both of them. A lot of the variables are the same, but there are a couple key differences. For a chi-squared test for independence, we know that we need to have two categorical variables, and therefore we would have a two-way table with rows and columns, multiple rows and multiple columns, that is. And then we're testing the independence of those two variables. Do they affect each other or not? The chi-squared goodness of fit test, it's only one categorical variable, as we mentioned, and it tests whether the results of that single variable are consistent with the predicted results that we have. And again, it's worth mentioning that when we say variable, we're not talking about a number that's varying. These are categorical variables, and so this would be something like favorite color, and that could vary between red and blue and green, but we're talking about statistical categorical variables, not like X and Y sorts of numerical variables. So again, I'm going to keep saying this, but remember the chi-squared goodness of fit test has only one variable, and that alone could be enough to determine whether we're using the chi-squared goodness of fit test or we're using the chi-squared test for independence, whether we have one or two variables. Chi-squared goodness of fit test has expected values. We abbreviate those as F sub E, just like we did for the chi-squared independence test. And we can get them two ways. They either must be generated, and that would often be from like a probability distribution, or they could just give us predicted values from a table or something along those lines. And again, then we're comparing the actual results with these predicted or expected results, hypothesized results. As with all chi-squared tests, each expected value must be at least 5 in order to perform the test. So whether we're doing the chi-squared test for independence or we're doing the chi-squared goodness of fit test, we need to make sure that any expected values involved in the process are at least 5. And if they're not at least 5, then it wouldn't be a valid test. The calculated chi-squared value or the chi-squared statistic is still found using the same formula that we used for the chi-squared test for independence. Similarly, we can use our p-value or the p-value test to get our results from the chi-squared goodness of fit as well. Just like the chi-squared test for independence, there are 6 steps, and they're very similar for the chi-squared goodness of fit test. We do start by stating our null and alternative hypotheses. Our null hypothesis, H sub 0, will always say that our data is consistent with what we expected, either consistent with our prediction or a specific distribution that was stated, but it's consistent. It's what we expected. It's the same as we predicted. And then the alternative hypothesis says the data is not consistent with our prediction or specific distribution. To get our degrees of freedom, this is also a little different from the chi-squared test for independence. All we do is say how many different options or categories within our variable that we have and simply subtract 1 from that. So like if it was dealing with color and there were 4 color options like red, blue, yellow, and green, That'd be 4 different categories or 4 different choices that people selected, and we would just subtract 1 from that to get our degree of freedom. Significance level is just like for the chi-squared test for independence. Again, that's telling us how much sort of tolerance there is within the test, how much wiggle room. And usually that'll be stated in the problem. Otherwise, we usually default to 5%. The rejection inequality works the same way as with the chi-squared test for independence. Once again, if chi-squared is greater than the critical value, which we obtained from a table of critical values, then we would reject our null hypothesis. If chi-squared is less than that critical value, we would accept our null hypothesis. And as mentioned on the previous slide, we calculate chi-squared the same way, or we can use the p-value from the calculator. And then we either accept or reject for step 6 our null hypothesis, whether our chi-squared value was higher or lower than the critical value, or if our p-value was higher or lower than our significance level. So especially towards the end of the test, very similar to the chi-squared test for independence. So let's take a look at an example now. In this example, a school predicts that the number of absences for its senior students are consistent, regardless of the day of the week. And senior absences for 1 week are recorded below. So what do they mean by this? They just mean that we're expecting to have about the same number of absences every day, regardless of whether it's Monday, Tuesday, Wednesday, Friday, whatever. That's that word consistent right there. Now, if we look at this data, you might be saying already, well, it's not. They're different. From Monday to Tuesday, we've already varied by 2. Went from 10 down to 8, and now we're back up to 11 on Wednesday, and then it was consistent to Thursday, and then Friday we went way up. But they don't need to be exactly the same. What we're just asking is within that certain tolerance, that certain significance level, are they roughly in that same ballpark? And again, by adjusting the significance level, that could, determine whether we want to be, more strict with our test or less strict. But for our purposes, again, the significance level will be given. So we're just saying, is this a good enough fit? And again, that goes with the name of the test, the goodness of fit test. Is this pretty consistent from day to day within a statistical viewpoint? So let's start by answering the first question. It says the school will test the prediction with a goodness of fit test. Write down the null hypothesis for this test. So let's go back to the prediction. What are they predicting? The school predicts that the number of absences for its senior students are consistent regardless of the day of the week. So we're expecting the number of absences to be the same each day of the week. So we can phrase that as our null hypothesis, abbreviate that H sub 0, and senior absences are equally likely each day of the week. We could have also just stolen the wording straight from the problem. Seniors absences for senior students are consistent regardless of the day of the week, but I think this is a little more clear. Senior absences are equally likely each day of the week, and that would be our null hypothesis. It didn't ask for it, but our alternative hypothesis, H sub 1, would state that senior absences are not equally likely each day of the week. So just by adding that word not, we can turn it into our alternative hypothesis. Moving on to part B, it says write down the expected values for this data. Well, what were they expecting in this problem? They were expecting that all the absences were the same. Well, how many absences would that be? So the first thing that I'm going to do is add up all the absences that we had in this recorded data here. So we're going to add up the absences for Monday, which were 10, plus Tuesday 8, plus the 11, and then another 11, and then the 16. Add them all up and then divide by 5, because we had 5 different days of the week to figure out what the average would be, and that's what we would expect if they were all the same. So that work would look like this, where again we're adding up the 10 plus 8 plus 11 plus 11 plus 16, and then dividing that sum by 5 to get our mean or our average. And we would expect all 5 days to be 11.2. Obviously, you can't have 0.2 absences, but that would be the idea. That's what we would expect based on this data. So now our question when it comes to the goodness of fit test is, are we in the ballpark of that? Are we close enough to say that, yeah, our actual results are are consistent with these predicted results? Before doing the test, we need to get our degrees of freedom. And so again, for this, all we're doing is looking at how many different categories we had for this variable and subtracting 1. Well, we have 5 days of the week: Monday, Tuesday, Wednesday, Thursday, Friday. So we have 5 different options or categories for this variable, and we're going to subtract 1 from that. So we'll do 5 minus 1, which gives us 4. So our degree of freedom for this test is 4. And now finally, with all that information, our degree of freedom and our expected values, we're going to test our prediction using a goodness of fit test and a 5% significance level. So I'm going to be focusing on using the p-values rather than a chi-squared value, but we could also do this, using the chi-squared equation and get our critical value. So let's talk about how to get this all into our calculator to do it that way. So unlike using chi-squared tests for independence where we use matrices, we are going to go to stat, and this is more like how you would enter in values for correlation or one variable stats or something like that. So we're going to go to stat on our calculator and then edit, and that'll get us to our lists. And you can see I've already got the numbers in here, but I'll show you how I put those in. Again, we can clear a list by highlighting the list and then arrowing down or pressing enter. So our first set of numbers here that we have was the actual recorded data. So that would be our observed data. That goes into our first list. So 10, 8, 11, 11, and 16. Okay, so our 5 different pieces of observed data. And then in list 2, we're going to put in our expected values. And we expected 11.2. That was our average for each and every day. So we need to make sure to put that in 5 times so that it matches up with our 5 observed data values. All right. Now I'm going to quit out of this, second in the top left corner, and then quit, which is the alternative option for the mode button right next to it. Now I'm going to go back to stat, and then I'm going to go to tests. I find I can get there faster if I scroll up. And we see there's 2 chi-squared tests, and that's the independence test. And the one right below that, GOF, that's goodness of fit test. That's the one that we want. So I'm going to press enter. And you'll see on my calculator, it defaults to L1, which is great because that's where I put my observed data. And then my expected data, it defaults to L2. If you put it somewhere else, you'd have to let the calculator know at this point. And then we need to indicate our degrees of freedom. So our degree of freedom was 4. So you actually have to put that in for the calculator. It's not going to give it to you. And then we go ahead and calculate. And so we have a chi-squared value, and so if we were using our table of critical values, we could compare that to our critical value, and if chi-squared was less than our critical value, we would accept our null hypothesis. But I'm going to focus on the p-value instead. Our p-value for this test is right here, 0.540. And with that, we're comparing that to our significance level, which was 5%. Remember, p-value test is sort of the opposite of the chi-squared value test, where we are looking for our p-value to be bigger than our percentage for the significance level. And if our significance level is 5%, that's like 0.05 as a decimal, and we have 0.54. So our p-value is way bigger, so we are definitely accepting our null hypothesis. So for our final conclusion to the test, we can say that the p-value of 0.540, 3 significant figures, is greater than the significance level of 5%, or 0.05. Therefore, I accept the null hypothesis. Senior absences are equally likely each day of the week. All right, looking at example 2. In this case, a teacher predicts the distribution of passing grades on the final exam and compares them to the actual results using a goodness of fit test. So we can see over here on the left, we have this prediction, and this teacher is predicting that with their passing grades, 25% of them will be A's, 30% will be B's, 35% C's, and only 10% will be D's. And this is a probability distribution because if we add up all these numbers, we should get 100%. And you'll notice that unlike the previous problem, we don't have them all being equal. They are different. We're expecting a different number of A's than we are B's, and the most we're expecting is C's. So then we're comparing this to our actual results. So our actual observed data is over here, where we got 7 A's, 7 B's, 5 C's, and 1 D. And we want to know, again, is this within that level of tolerance, within that predicted distribution? So the first question is saying, state the null hypothesis. Well, the null hypothesis always says that we are consistent. Our results are consistent. So in this case, we could say something like our null hypothesis is that the passing grades fit the predicted distribution. And again, those would be those percentages that we had listed there on the left. And our alternative hypothesis would be that the passing grades do not fit the predicted distribution, had they asked for that. For part B, it asks for the degrees of freedom. And so once again, we look at how many different options or categories there were for this variable, which is the grade on the final. And we can see there were 4 different passing grades. So we're going to do those 4 minus 1. We always subtract 1 from our number of options or categories to find our degree of freedom. And so 4 minus 1 gives us 3. So we have a total of 3 for our degree of freedom. Now we need to do our expected values. So we have percentages going on here with this, this distribution. And percentage of the class, right? 25% of the class. Well, we need to figure out how many people are in the class, or at least how many people are in the class that got a passing grade. So what we'll do is we'll take all of these frequencies and we'll add them up. And so 7 plus 5, when we add all that up, we get a value of 20. So we know there are 20 students in this room, or this class, and 25% of that 20 would be the ones we expect to get A, and then 30% of that 20 would be the amount that we expect to get B. So we can go through and do that math, and I'll show that right here. So our total students, again, is 20. We got that from our actual observed data. And then we can see that 20, which is our number of students, times 0.25, which is like 25%, gives us 5. So there are 5 that we expect to get A's, and then 20 times 0.3, or 0.30, would give us 6. So 30% of the class would be 6 students. That's the amount we'd expect to get a B. And then 20 times 0.35, or 35%, would be 7 students, getting a C. And then finally 20 times 0.10, giving us 2. Now if we look at this, I mean, none of these numbers are that far off, but also none of them are exactly what we predicted either. So again, the point of the goodness of fit test is to determine, are we, consistent with the prediction? Are we in the same ballpark? However, when it comes to doing the actual test or stating this conclusion, though we could go through the process of doing the test, we don't really need to, because if you look at our expected values, we have 5, that one's okay, and we have 6, and that one's okay, and we have 7, that one's okay, but then we have our last expected value being only 2. And remember, in order to successfully do a chi-squared test for independence, or in this case, a chi-squared goodness of fit test, we need to have expected values of at least 5 or bigger. So the original 5's okay, that's the lowest it can be, but that 2 that we had for the number of expected D's is not okay. So we can say that the test cannot be applied because not all expected values are at least 5. All right, and with that, we are going to conclude the lesson for today. Till next time.